Vladimir, Skavysh again, everyone. After initially working on theories of dark energy, he switched to deep learning upon seeing the AlphaGo versus Lee Sedol match. He has subsequently joined Canada's central bank to work on the areas of big data and machine learning. Not long after that, some opportunity arose to lead the Bank of Canada's exploration into quantum computing, and he's currently originating, strengthening, and executing quantum proof of concept projects and quantum collaborations between Bank of Canada and industry, academia, government, and other central banks to find areas with central banking that might benefit the most from quantum computing. And with that, I'll just pass it on to Vladimir.
Okay, awesome. I have the distinct pleasure of talking to you guys at 8:30, tender hour. I remember watching another talk at some point, and the presenter started with a poll of how awake the audience is. It was something like, yeah, I'm ready to go. You know, starting to doze off a little bit, and then just please don't torture with mathematics. So how are you guys doing? Great. I didn't hear that. Let's try it again. Are you ready to go? Yes, yes, exactly. Because my subject will be breathtaking, I guarantee it. Okay, well, so far, private companies have dictated to a large degree the narrative about quantum applications within the real world. We have big banks, private banks promoting portfolio optimization, pricing of options, and such questions. Big pharma and healthcare and chemistry and so on, they care about protein folding, about drug discovery. Energy companies, they care about battery design. Logistics cares about finding the quickest route, so on and so forth. Therefore, you might be surprised, perhaps, to learn that there is great excitement in the public sector for quantum computing. Of course, we approach quantum also from the point of view of concern about Shor algorithm breaking the RSA encryption and much of our modern encryption schemes. We care, of course, about other countries possibly overtaking us on quantum research. But ultimately, it's excitement that drives us about the applications, about the benefits that quantum computing can bring to us. So today I'll talk to you a little bit about economics applications, and economics is not finance. I'll clarify that a little bit. And more specifically, I'll talk to you about the applications that we see at the Bank of Canada, and how we ended up working on quantum, and what kind of work we've done and plan on doing. Briefly about myself. Of course, my thunder was stolen, but very briefly, I started in physics, and briefly I worked on things like, for example, dark energy and detecting dark energy with neutron interferometry. But then I recovered. In 2016, I saw the Lee Sedol versus AlphaGo match, and I myself play Go, and there was belief that it would take at least 10 years to reach this kind of level. But here, the computer handily beats the world champion. At that point, I realized it's time for change, that I want to join this revolution of data science, machine learning, deep learning, solve some exciting new problems, publish papers that can potentially transform the whole field in a single kind of go. But I needed a job, and the Bank of Canada was able to offered to hire me to work on big data, as well as applying machine learning to problems within the bank. But my background in physics actually opened a very interesting opportunity for me. At some point, Bank of Canada joined the CDL program, the Creative Destruction Lab, which is essentially an accelerator for startups. And they've got multiple streams. They've got space, they've got medicine, crypto, and they've got quantum. And my colleague and I, the colleague soon thereafter left the bank, but we attended one of these events and realized, talking to some of these companies, including Agnostic actually, that the ecosystem has grown to the point where, and both the hardware and the ecosystem, where it's time to start experimenting with this technology. So that's, and because of my background, I was in a unique position to actually take advantage of that, not just appreciate the development, but also actually go ahead and start working on this myself. Initially, it was a volunteering kind of effort in my spare time, trying to figure out what kind of applications the Bank of Canada might see from quantum. Luckily, this coincided with the digitalization efforts at the bank, which means using all sorts of emerging technologies, like deep data, new sources of non-traditional data, machine learning, deep learning, robotics, all sorts of other AI, green technologies, and so on and so forth. And I was able to, through this program, apply for funding and through some other sources and launch the Quantum Lab. We hired some interns, including Maggie and Lana. They were actually our first interns, the girls that are co-organizing this conference. And then Rain is in the audience as well. He'll talk to you tomorrow at the careers panel. And if you actually would like to find out more about how the work was like during those early stages, Lana wrote an article, a Medium article, about this that goes into some detail as to how it was very, very early on, where we were just starting out, didn't really know much, didn't know what the hardware exists, software, and so on and so forth. Okay, before I proceed to some of the projects we've done and applications, perhaps it behooves me to tell you a bit about the Bank of Canada. First of all, we're not a private bank, we're a central bank. So in other words, in particular, that means we don't really care about making money. In fact, if we do make money, we give it all away at the end of the year to the finance department. Instead, our functions are monetary policy, which is essentially controlling inflation to be low and stable and predictable. It's ensuring the health of the financial system, which means being a lender of last resort, overseeing all kinds of clearing systems and settlement systems, these kinds of things. Also, we produce banknotes, so the paper money that you have. Not the coins, though. That's the mint, Canadian Mint, that does that. Perhaps in someday we'll be also in the business of CBDC, central bank digital currency, but that's up to the government, up to the politicians to decide. Okay, and then also we provide funds management. So basically, the government, we're the government's bank. Government needs to raise funds, sell securities, so on and so forth. That's we are the ones who do that. And now recently, we've also acquired a new responsibility, which is to monitor retail payment systems, which includes all kinds of innovative payment systems out there. There's something like 2,000 of them. So as I mentioned, there's a clear distinction between us and the private bank, and in particular, we don't care about money. And so what happens sometimes, quantum companies who are not aware of these differences actually come to us and tell us that if we're interested in estimating the price of options. That's great. We have finance people as well, and it's of interest to them perhaps, but that's ultimately not what we're about. We want to ensure welfare, financial and economic welfare of Canada. That's our main objective. And then, but why is a public institution like Bank of Canada looking into quantum computation? At the end of the day, the simple answer is that we're big believers in innovation. We saw firsthand how the digitalization efforts, deep learning, big data, cloud computing, so on and so forth, have transformed our institution, how much it benefited us. And so we have a deep belief that by investigating other emerging technologies, someday we might see similar benefits. And in preparation for this, for when this comes, in terms of quantum, we're developing our internal workforce within the bank who can understand these problems and the applications. We also are establishing external partnerships with companies, with academics, with other central banks and public institutions to work on quantum projects. And also, of course, we care about post-quantum security to make sure that our central bank digital currency, if it ever comes out, is crypto is quantum secure, or at least quantum agile, as well as a host of other cryptographic systems within the bank, of which there are something like 100, that they are also not vulnerable to quantum attacks. Briefly, I won't be focusing on the post-quantum, but of course it's a big part of our work. Currently, NIST is trying to, those are purely classical algorithms, which, however, are supposed to be difficult for quantum to solve. So quantum may solve RSA encryption, for example, but not some of these. Well, and NIST is trying to find these algorithms, but already a bunch of them, those crossed out by the red lines, have already fallen out. So it's actually not easy. And then the yellow ones are already under risk. Okay, and then I mentioned that central bank is not the same as private bank. Well, so the same is kind of true about finance and economics. They have a common origin, and there's an overlap there. But ultimately, the literature of economics and what it is about is ultimately different. So as I mentioned, pricing options, well, that's not really us. Okay, so what are some of the economics applications? The two big ones, I would say, or maybe, well, let's go through them in order. Maybe the biggest one, perhaps, is solving economics models. So, okay, going back again to our main function, we want to ensure welfare for financial and economic welfare for Canada. So what does that mean? We need to be able to understand what the economy is doing right now, what it might be doing in the future. So that means we need to be able to solve a complex, take the various data sources, use our economics theory about what this data tells us about consumer behavior, about how firms are, if they're under stress or not. Is the economy overheating, or is it actually slowing down? If we understand that, and moreover, if we understand how we can influence the economy, then we can intervene potentially, let's say through our monetary policy. And so we've got these huge models like Totem 3, for example, which we use to essentially estimate the behavior of the economy and what it might do in the future. But solving these economics problems is a really challenging problem. And there are lots of all these kinds of models. But briefly speaking, there's a number of quantum algorithms with proven theoretical speedup that can help. Function approximation, linear system analysis, Monte Carlo, which I'll talk briefly about later, matrix inversion, linear regression, interpolation, numerical differentiation, true random number generation. And then there are also algorithms like within quantum machine learning, for example, or quantum optimization, which don't necessarily have a proven theoretical advantage, but perhaps empirically might be shown to someday give some kind of a quantum advantage. And there are lots of these, but I guess I'll mention some of them later. Another interesting application, which is a little bit further down the line, is quantum money. So in particular, there's a quantum theorem of no cloning theorem. And what it means that, essentially what it means in practice within this context, is that we can create money that simply cannot be counterfeited. And the proof is not, and the proof is physics, in the physics. So the physics guarantees that the money cannot be counterfeited. Because as soon as you change the money a little bit, then the quantum state of the money changes, and therefore it's not already the same money. And this basically can be observed. There are lots and lots of these schemes. I mentioned some of these. If you would like to learn more about the subject, there's a long paper actually from Isaiah Hall and his co-authors about quantum money, summarizing the literature. Another application is data processing and analysis. As a central bank, we collect all sorts of data. That includes non-traditional data like text data, tweets, newspaper articles, so on and so forth. It includes tabular data and basically credit data, like credit cards, mortgages, all of these things. We collect data about purchases by consumers in in stores, for example, things like that. Actually, that's Canada collects, but we take advantage of that. I'll highlight maybe two things within this. So basically, we collect lots of data, and so if we can develop tools for processing the data and then analyzing it, then that will be beneficial to us. And I'll highlight two maybe recent advances. One is the Nature paper, I guess Nature physics paper, where they've shown rigorously, well, through mathematics, that a quantum can learn correctly and efficiently the distribution of logarithmic, discrete logarithm data, whereas classical would struggle with it. For classical data, it'll all look like noise, but quantum can actually efficiently learn this with exponential speedup. So that's doesn't guarantee that all other data can be efficiently learned, but this one in particular can be. And so this gives hope that maybe there are some other examples as well that are more useful. Another example that I'll highlight is within natural language processing. As I mentioned, we've got all kinds of text data. Tweets, newspapers, speeches by politicians, speeches by company owners, reports from companies, and so on and so forth. Taking advantage of this means because it's such a huge amount of data, taking the most advantage means using deep learning currently, but in the future, in fact, maybe quantum can help us with that. The challenge is that current NLP models, really what they reduce to effectively is you take the whole of the internet, you take a neural network, the biggest you can possibly get, like one containing 1.6 trillion parameters, you stuff the internet into those parameters for training, you spend $10–20 million, weeks and weeks of thousands of GPUs and CPUs working on that, and then you get some kind of a state-of-the-art results, which however still is quite far away from what true language is. And it's clearly not how we humans, who are doing really well with language, treat language, how we approach it, how we learn it. And maybe, perhaps the problem is that the models that we're using are not quite ideal. For example, we're not really taking advantage of the structure of language, the semantics, the grammar, so on. How closely the words are associated, not explicitly anyway. And quantum here might actually offer an advantage, potentially down the line. There's this DiscoCAD model, this one. The different words are represented as multi-dimensional tensors, sort of like currently within NLP. Then these different lines, they define the logic of how these tensors are to be combined, essentially how they are to be reduced, multiplied, however you want to think about it. But the problem with this, you end up with a huge tensor neural network structure that cannot be efficiently solved by quantum. This thing blows exponentially. So maybe you can handle mid-sized problems, maybe paragraphs. But handling whole books, that becomes not computable, classically. But quantum has the potential to eat tensor networks for breakfast. So without really going into the details, let me just leave you with that. The future of NLP could well be quantum someday. And now maybe let me tell you briefly about some of our projects that we've done at the bank. We've been doing them only since recently, so the results are just now coming out. But this is a paper with Xanadu that we've done on using quantum Monte Carlo to solve some economic models. And there are two models that we've solved in the paper. First model is we've got some banks. They've got a capital ratio, which is mandated by the government. Basically, how much safe assets they have to keep that they can sell in case of trouble. They've got some debt and assets. But then what can happen is some kind of an economic shock. The assets lose value, so let's say mortgage crisis. Mortgages are not worth as much. This ends up having the effect of dropping the capital ratio below 3%, which is the required number. Then the banks, to rebalance themselves, have to sell some of their assets. And through this, they get back to 3%. The problem is, as they sell the assets, there are fire sale losses. So basically, lots of people are trying to sell at the same time, which plummets the price. And so what ends up happening is that actually their capital ratio is not 3%, but actually, let's say 2.5%, because the value of the assets, because of the selling, dropped as well. And so this ends up being this kind of non-trivial sequential or multi-time period problem. And Monte Carlo is one of the approaches used to solve this kind of thing. So we thought, okay, let's try quantum Monte Carlo. And we were able to actually apply it for this problem, get an answer that's very close to the true value. And then the other problem we solved was in a neoclassical growth model. Essentially, you've got productivity, or let's say innovation, and the agent, let's say a firm, tries to decide how much of the money that I have now, how much capital, am I going to invest, and how much am I going to, let's say, use right now, like save for future. Yeah, and so there, these kinds of models actually become extremely difficult to solve as you keep adding variables. Like below 5, we can solve them okay. From 5 to 25 variables, that's already really, really tough, and you need some splines or some advanced kind of approximation methods. Beyond that, the only solution really is deep learning, so far at least. And that's a recent development as well. And within this deep learning approaches, there are some challenges. One in particular is how do we handle stochastic variables. So in other words, we can estimate what the technological development will be in the future, but we can't be certain. It's only in the future that we realize this technological breakthrough. So we need to account for the stochastic nature of, let's say, technological innovation. So different possible futures. In practice, what this means is that within the deep learning routine, there is a complicated, laborious and time-consuming Monte Carlo simulation. And again, we thought, okay, let's see if quantum can speed it up. Of course, quantum Monte Carlo currently cannot be run at scale. It can only solve really trivial problems. But we can simulate it to get at least some form of, to estimate when approximately quantum might have an advantage over classical Monte Carlo. And we ended up with this plot, depending on gate times, so basically how quickly quantum computer works. We can already see benefit for computations, let's say, in this optimistic, let's see. So this is the classical, right? This line, and then these are the quantum lines depending on gate times. In the very optimistic case, we can already see benefit with computations of less than, approximately a tenth of a second. And these times are actually not that optimistic. They're quite realizable, I think. The problem here is depth with these algorithms. You end up needing like 10,000 gates at least, if not 100 or more thousand gates in sequence. And so current computers simply cannot run it. We'll need a fault-tolerant computer, which is 5, 10, 15 years away. Okay. How am I doing on time? Okay, good. Another project. We haven't published the paper yet, but we've presented it at several conferences, including at Qubits last year, at least the early version of the work. But the idea is that in the real world, everyone's not connected to everyone. Instead, we've got some kind of a network structure. You can think of social networks where some people know other people. In financial markets, that means some firms trade with other firms who trade then with other firms and so on. This can lead to all kinds of, how to put it, complicated network structures, which then, depending on the structure, actually will have a different result on how the economy will behave. So in particular, a common question is, suppose one bank, let's say, or one institution, one firm, defaults, like bankrupts. So what could happen is that, okay, institution B, they need to pay institution C, and expect payment to be able to do so, expect payment from institution A. But institution A bankrupted, so suddenly institution B cannot make its payment. And then maybe institution C might not be able to make its payments as well. And so with one potentially big institution like Lehman Brothers, the whole system can potentially grind to halt and maybe even come to the brink of collapse without governmental intervention. So anyway, these things actually turn out to be quite challenging because of the scale, but also because of the theories that we have. to deal with economic networks. Here, for example, let's see, can you see this? No. Okay. Here, for example, we can see there are 3 players, P1, 2, 3. But to be able to understand how they end up connecting in the equilibrium, so like at the end, if we solve the game, who will be connected to whom, we need to effectively consider all the possible states. And this ends up being 2 to the n squared. So let's say for 3 it will be 8, for 4 it will be already, what, 64? And then it grows super exponentially. Yeah, and so anyway, in this project with Multiverse, we used quantum optimization, essentially quantum annealing or simulated annealing, to be able to find this optimal state of the economy without actually going through each of the possible states. So basically not a brute force, but rather have the quantum find the optimal state in a single go, so to speak. And we applied this to a cryptocurrency market to see how adoption of crypto depends on the network structure. Another recent work, which we will be publishing actually shortly. It's on natural language processing. As I mentioned, quantum could be the future of natural language processing. And so we've started this journey at the bank. This doesn't involve DiscoCat or any of these complicated models, but rather we investigated kernel methods, kernel SVM, as presented by Agnostic. We investigated transfer learning, where you take, let's say, classical NLP model like BERT, or GPT-2, or whatever your favorite flavor of the month is. Then the idea there is the neural network will reduce the amount of features, which is a big thing for quantum because of how few qubits there are. So basically, you've got all this rich feature, thousands of words. How do you use, let's say, 20 qubits to represent this in a huge feature space? You simply cannot. You need to drop a lot of information. So one way around this is to use classical pre-processing, like a neural network, which will, on the one hand, reduce the feature space, on the other hand, extract useful features. Then a quantum layer can be added to that, like a quantum variational circuit of some sort. And the idea being is that hopefully the quantum part can learn something much more efficiently or quicker or better or cheaper than a classical layer would be able to do at that point. And so that's actually what we see here. This is, on the one hand, is classical computation. So basically, we constrain the number of qubits to 5, let's say, or 4 or 8, and had an equivalent structure where the quantum layer was replaced by a classical layer with the same number of learnable parameters. And in this case, we can see actually quantum learning potentially quicker. So the blue line, it achieves maximum quicker, and also ends up being slightly higher accuracy, at least for a small amount of data. When there's lots and lots of data, then classical actually seems to be at least as good or better potentially. We're not claiming quantum advantage, but it's an interesting result nonetheless. Okay, and then recently on Archive we released a paper about optimizing payments system. So the central bank is in the center of a network of 16 players, well, big institutions, and they sent trillions of dollars of payments to each other over the course of days. Or I forget how much was the volume is, but it's very big. And the idea is that these payments have to be prepaid, meaning that you cannot just IOU a payment. You have to have this money in the system. This means either you make a deposit directly to the Bank of Canada, which means you lose that money for 2 days. So that's the amount of settlement time, which you cannot invest, earn profit, or you actually have to even borrow it for 2 days, and then you have to pay interest on it. The other strategy is to wait for somebody else to send you the money, and then use that money as collateral for the payments. And so it becomes a challenging optimization problem. from the perspective of the financial institutions. Do we make the payment right away? Or do we wait a little bit, hoping to earn some extra profit? But in this paper, we actually approach it from the central bank viewpoint. The central bank thinks, okay, we've got more information than anybody. All of the banks, you guys send us what kind of payments you'd like to make. So maybe we can do the optimization on our end. We'll take all of this, let's say 70 or 100 or however many payments. We'll put them into, let's say, a quantum optimization scheme. And let's see what kind of answer we get from that. Like what's the right order of payments to minimize the amount of money that needs to be deposited to the Bank of Canada. Why exactly quantum optimization? The algorithms, like the payments, QE, it turns out to be an NP-hard problem, and it grows exponentially. Classical algorithms, likewise, therefore have to grow exponentially in how quickly they can solve it. Moreover, actually, current algorithms in use are not particularly good, classical algorithms. I think if we spent a decent time working on it, we could come up with something good, but right now they're not great. So we thought maybe we can, with quantum, deliver some good speedups, good improvements in terms of liquidity. And this is what this, this table shows. I guess you cannot really see it. But at the end of the day, on average, we're saving some like $240 million in transactions every day. Okay, and then the most recent work with agnostic. Hi guys, wherever you are. Here, of course, we've got a lot of time series data. Financial markets, stock markets, option prices, debt markets, and so on and so forth, as well as economic markets. So how things change over time within the economy, what people's purchasing behavior is, how is the debt, individual debt changing over time, credit cards, mortgages, so on. All of this is time series data. And we need to have, keep developing tools to help us work with such data. Machine learning has a number of such tools already, of course, but a lot of them suffer from the curse of dimensionality, where the more features you have, the longer the time series, then the time to compute, to solve the problem, ends up growing exponentially. Or alternatively, maybe just the models aren't that great at the end of the day. Maybe we need something else, kind of like with the natural language processing. And so here, this is a proof of concept. So we didn't really try to prove that this is better than anything else. Rather, we wanted to show that we can use a quantum computer. And we used a real IBM computer for this, IBM quantum computer, to show that we can predict anomalies within time series data and to classify time series chunks as accordingly, whether they're anomalous or not. So in particular, we had the cryptocurrency data, basically trading data from Binance. We had Bitcoin versus USDT. And thankfully, we can, well, interestingly, we can observe movements on the blockchain. So basically, is there a huge transfer of Bitcoin, let's say, or USDT to Binance, or let's say from Binance? We know that from the blockchain. And then the question is, can the algorithm, just looking at the trading data, can the algorithm detect that there's a change in trading pattern? So because we know the actual movements of currency from the blockchain, we can know if some series should be anomalous or not. And the algorithm actually does its thing. It's actually able to predict it correctly. I don't want to go too much into detail because we've not released the paper yet, but stay tuned for it in 1, 2, 3 weeks. It will be out on archive. I'll briefly mention some future directions of work that we're thinking about. One thing is, again, for solving economic models. One big subject is economic games. So there are players, and they try to optimize their, let's say, return on money, profit somehow within the economy. They interact with each other, and so they end up solving this reinforcement learning problem. Kind of, what is my best action given the current state in the environment, such that I benefit the most? And each of these agents has the same kind of, or similar, maybe they have actually different goals. If there's a central bank, then the goal of the central bank is actually quite a bit different than the agents. But anyway, it has a goal as well, and it's trying to optimize that goal. So currently, there are various methods within standard economics, like linear programming, to solve these kinds of games. But reinforcement learning, like with with AlphaGo, can offer big improvement. The problem there with with reinforcement learning, it requires huge amounts of data, huge amount of cost. And so quantum might be able to overcome that. Maybe we can train the data quicker. Maybe we need fewer examples. Maybe we can find the optimum much faster. Briefly, I'll mention another possibility is using quantum graph neural networks to study economic networks. And also, let's say, for example, extend the quantum Monte Carlo work we've done to a Markov chain Monte Carlo type of algorithms to solve more complicated problems that depend on past outcomes. Okay, and in conclusion, there are many applications within economics and central banking. And moreover, there are many applications within public institutions, which might be a surprise to you. And so the future in quantum is bright from all directions. Thank you. Any questions?
Okay. Do you believe that one day the quantum machine learning will actually outperform classical for large cases quicker and more accurately?
Well, if it ever outperforms classical computation, it most likely would need to be on a large scale, because I mean, small scale problems simply aren't interesting. So even usually, there are some maybe extreme cases where maybe you've got 50 points of data, and then maybe quantum can actually do better. But in most applications, yes, the problem is we've got huge amounts of training data. Let's say, as I was just saying, reinforcement learning. Well, let's say to beat Lee Sedol, they needed millions of games, thousands of GPUs to compute over all of that. Quantum can potentially do better than that. So as far as I know, there aren't any concrete proofs yet, but this is the story of machine learning as well. We oftentimes don't have proof that it is better than than other algorithms. To the contrary, there's actually some no free lunch theorem, for example, which says that actually just about any algorithm may perform as well on random data. Turns out that real data isn't random. But long story short, empirically, we were able to show that machine learning can significantly outperform other current algorithms. And so the hope within the industry, for the most part, is that quantum machine learning might do the same.
All right. A little bit of a sidestep from what you're talking about, but I've heard of a very funny concept about applications of quantum field theory in modeling finance. Have you ever heard of any of that? And if so, might that find some other way in which you can utilize quantum computing to, say, use those models in particular?
Well, I would need to see the paper to know exactly what the paper is talking about. But my assumption is that it probably uses the Feynman integral formula. So essentially, the idea in Feynman interpretation of quantum mechanics, or maybe restatement of quantum mechanics, is that classical particle, well, takes one line. So let's say you've got a ball, right? You throw it, it drops like that. But quantum mechanically, it actually can take all of the possible paths. It's just that some paths are more likely than others, and then they can interfere with each other. And as the size of the ball, let's say, grows, for example, then we become more and more classical, and then all the additional paths end up canceling each other, and we end up with the classical path. So the idea is there, okay, so that we essentially investigate all the possible paths through through the system, which can be like future outcomes, for example. If you have an economy or finance, then there are all kinds of paths that option, let's say, can take. So my assumption is that this is the situation, that that's what they're talking about, that we can maybe solve these kinds of Feynman integrals to potentially tell us something about how the markets, some options, let's say, might be priced. Okay, let's assume that that's the case. I think there are some papers about solving quantum field theory with a quantum computer. I cannot state any at the moment. I would need to look it up, but I remember seeing some. So yeah, we'll see, hopefully. As far as other applications, well, economics, we've got all kinds of uncertainty or kinds of stochastic variables that we need to model. Who knows, maybe Feynman integral is the way to go.
So in your profile, you mentioned that you made the switch from physics to data science to finance. So like, could you talk a little like how you made the switch? Because that's like a bit of a, well, let's say, different track than most physics PhDs would go.
It would be right. It would be physics, then finance, then data science, right? Okay. So first of all, not finance, but economics. As I was kind of mentioning there. So that's one thing. But second, Bank of Canada needed somebody to, needed a data scientist. And I had some skills. So I applied and got a job. So that's that part of the transition. But then, of course, when quantum came along, then I conveniently positioned myself to end up in that niche rather than pure economics. As far as data science, well, problem with physics education, at least when I was in school, there was no emphasis whatsoever on programming. To the contrary, the mindset of a theoretician like I was is that, okay, you're expected to sit down with a piece of paper and pen and over days, months, derive some complicated equations on a piece of paper. And then, it's the end, maybe you get some kind of a breakthrough. In practice, that's not how physics is done these days. Relatively few people do such things, and relatively even fewer of them are actually successful in that. Vast majority of people now use computation on a daily basis, within theory, within experimentation, and just throughout physics. Machine learning is a big thing in physics right now. Deep learning, solving physics equations through nonlinear methods like function approximation, like neural networks. So anyway, long story short, I had zero programming, essentially. All the programming that I had was self-taught. And so I didn't really even know that I was good at computers. But as I learned about the field, I realized that actually this is my calling. Yeah. Plus, I'm really excited about AlphaGo and things like that can play really good games.
So about the anomaly detection project you just mentioned, I have a question that do you think that with the usage of quantum computing as well as like machine learning ways like SVNs, and the central bank will have a way to detect most of the major cryptocurrency transactions? Will the central bank have a way to identify all the transactions using cryptocurrencies?
So yeah, okay. So the question, I guess, if I understand correctly, is that cryptocurrencies are supposed to be partly, at least, anonymous, right? And so, central bank, but maybe some evil governments, will they be able to decrypt essentially this information and then punish people for doing that? Okay. So first of all, to some extent, that's actually a different question. So the first question is, what kind of cryptography scheme is the crypto employing? So if it's Bitcoin, for example, or maybe some of the most cryptocurrency, at this point, at least to some extent, they are vulnerable to quantum attacks through Shor algorithm, for example. So these things will need to be updated. Once this is done, there is assuming that the post-quantum algorithms hold, there's no reason to think that anybody will be able to use quantum to decrypt these transactions. As far as machine learning, analyzing blockchain data is a big thing. It's called chain analysis, right? Blockchain analysis. There are companies doing that, earning big bucks. They're working for the FBI to try to figure out all the bad guys and so on. So there's definitely folks working on that. Will quantum be of advantage there? Well, who knows? Depends on what kind of methods they're using, and we'll see. It's not something I personally worked on, so cannot really say more than that, but like anything with quantum, time will tell. Okay, you guys were an awesome audience, and I guess I stayed a little bit longer than I intended, but hopefully it was worth it. Thank you again.